Okay. Let's begin the class. I think we stop at the end of kinematics. Your lecture notes are posted. I have to update them a little bit to include the numerical methods completely, but for this lecture and next one, you can actually use you can use the current lecture notes. And your homework is also posted. It was very quick. Homework 1 posted. It only has 2 questions, very simple questions. And you have until Thursday next week. Thursday, which is going to be 20th, to submit the homework. But I would say get to it as soon as possible. It shouldn't take you more than an hour. It's pretty simple. Second question is a bit long, but it's just plug and chug. Just have to plug in the numbers and do the calculations. Okay, pretty simple. Any questions? Yes. Online. You have to. One thing about the homework that I forgot to mention. Whatever you submit, doesn't matter if it's a homework, it's a quiz. If you send it to me through email, it has to be a PDF file or Blackboard. Any other file is not accepted, right? I will tell you why. If you send me a Word file, or some people send me like 10 JPEGs, right? If you send me those files, I will reply to you, send me a PDF. And this will not happen a second time. You will get a 0 the second time, okay? But it is very messy. It is very hard for my graders, and it's turning a like Word to PDF is the simplest thing you can do. So make sure you just send me a PDF or upload a PDF file. Okay, so let's get back to the topic at hand. Today we are going to start by Newton's law of gravitation. This is a law you have seen before, and essentially relates the gravitational force between two objects by this equation. It says F of G, the gravitational force, is equals to G, which is the universal gravitational constant. Multiplied by the mass of the first object, mass of the second object divided by r squared, which is the distance between the center of gravities or masses of the objects. Okay? Who can tell me what is the value of G, the universal gravitational constant? Who remembers this?
Something times 10 to the negative 10.
Exactly. It's 6.672 times 10 to the negative 11. You said 11, yeah. And its units are meters cubed per kilograms second squares. What do we call this gravitational force when you are on Earth? Essentially, what is the gravitational force of Earth on you? What do we call this force? Or on any other planets?
Gravity.
Weight, right? Plain and simple. So weight is a form of gravitational force. The thing is, your one object is much smaller than the other one. So gravitational constant is going to remain the same. Mass of the bigger object or mass of the planet, we show it with capital M and a small m for mass of U, essentially, divided by the distance between you and Earth, the center of gravity of Earth. If you take the small m out, we are essentially multiplying m, your mass, by g, universal gravitational constant, multiplied by mass of Earth or any other planet, divided by this distance. So we can essentially say weight is equals to your mass multiplied by the gravity, right? Gravity is this. It's the definition of gravity. If you are on the surface of the Earth, gravity is shown by G naught. So gravity on the surface of the Earth. And G naught is universal gravitational constant multiplied by mass of the Earth divided by the radius of the Earth to the power 2. And we are to assume on the surface of the Earth, G naught is always 9.807 meters per square second. The question we want to answer here is this: how does gravity change with altitude? Or does it change with altitude at all? Yes, right? Because you can see here, it is a function of r. And when you increase the altitude, you are essentially, or change the altitude, you are essentially changing this r. And we want to find the relationship between g and the gravity on the surface of the Earth. It's a pretty simple calculation, but you'll end up with this relationship. So the gravity at any altitude is equals to G naught multiplied by the Earth radius to the power 2 divided by your altitude plus Earth radius to the power 2. So essentially you are to scale the gravity, the Earth gravitational, surface gravity with altitude. Any questions? Yes.
It's RE plus what?
Z. This is the altitude. Z is the altitude. It's essentially your distance from the surface of the Earth. Okay? So let's solve an example which is mostly related to the previous lecture's topic. It's a little related to this topic as well. So we want to show that in the absence of an atmosphere, so no atmosphere, we want to show that the shape of a low altitude ballistic trajectory, just reading off my notes here, is a parabola. And we are to assume G is constant and neglect the curvature of the Earth. So essentially, this thing in your trajectory is so small that it sees Earth as a straight line. Okay? How should we solve this problem? The first thing you need to answer is, what is a parabola? What is the trajectory of parabola? Let's say we found the trajectory. How can we say it is a parabola? It's a parabolic trajectory.
Well, it rises at it rises up until a point, and it reaches maximum, and then it goes down at the same rate that it was going up.
So yes, that's essentially,
That's a problem.
you have to plot it though, right?
Yeah.
Without plotting, just by looking at the equation for the trajectory.
And you could find its roots of the equation. Try to find if, if it has multiple roots to kind of determine if it has points of inflection.
So if it has 3 roots, is it still a parabolic trajectory?
No, but
Only
like 2 roots.
It has to have 2 roots. So essentially, it has to be a second order. Yeah, it has to be a second order curve, right? And what is a second order curve? Y equals to x squared, right? In those type of things. So we need to find the trajectory, and this trajectory needs to be a second order curve. Okay. Well, how can we find the trajectory? What are the informations we have?
Gravity.
The only outside force is the gravitational force, right? So the only acceleration is essentially the gravitational pull, right? The gravity, right? So let's actually have a coordinate system, x and y. You're also given this figure. We have a v naught, and this is the predicted trajectory. It is as location x naught and y naught. And we also have this angle, gamma naught. This is called the flight path angle. So the angle your vehicle has with the surface of the Earth, right? The trajectory of your vehicle at that specific location. So we only have the gravity, which is in this direction. What can we say about the accelerations in different directions? What is the acceleration in the x direction? 0. What is the acceleration in y direction? Negative g, right? Let's just use g. So using these, how can we find the trajectory? And this trajectory simply means the relationship between y and x, right? Just a function. Y is a function of x. The first thing you want to do is to integrate, right? Double integral. X double dot, and this is essentially dx, second derivative of x with respect to t squared, right? So we have to take the derivative with respect to x twice, which is going to yield this. X is equals to x naught plus v naught t, right? V naught in the x direction though. V naught of x. What is v naught of x? We have v naught. We want to find the projection of v naught in the x direction. Exactly. V naught cosine gamma naught. We should do the same thing for y. Is going to be equal to y naught plus v naught yt minus 1/2 g t squared, right? These are the equations of motions. They are the very famous equations of motions, right? For accelerated motion. V naught y here is going to be v naught sine of gamma naught t. So we have the equations of motion in two directions as a function of t. But here we want to find the trajectory. So we need to find the relationship between x and y. How can we do that?
Solve x as t, solve x for t, plug it in y.
Exactly. So we are going to use this equation, solve for t, whatever that is, and then substitute t with that equation essentially in our y equation, which eventually is going to give you this trajectory. Y is equals to y naught plus x minus x naught tangent of gamma naught minus 1/2 g over 2, I'm sorry, v naught squared cosine squared of gamma naught x minus x naught squared, and that's it. As you can see, this is a second order curve, which means that we have a parabolic trajectory. Okay, let's solve a second example, and this example is the first quiz. So I want all of you to take a paper, write your names on it, and you have, what time is it? You have 10 minutes. It's 10:24. Let's shoot for 10:30, like 4, to solve this. And I'm gonna write the text of the problem for you. We have an airplane that flies a parabolic trajectory like that, like the one you saw here. Okay, just a parabolic trajectory, and it is flying that trajectory in a way that the passengers will experience free fall. By free fall, we mean weightlessness. And we want to know what is the required variation of the flight path angle with the speed. So we're going to find the function gamma naught essentially. and you are to ignore the curvature of the Earth.
So we just care about the vertical velocity, not the tangential velocity?
I mean, you have to care about acceleration in general, right? Well, vertical velocity, and you just solve the problem. I'm pretty sure you can solve it. It's pretty simple. So this is the direction of the flight. Then at the second time, it is going to be like this. We have a d gamma at two different points. Let's say that's the center of this curvature. We have a d phi. This is also rho, the curvature of the Earth. And the flight path angle, gamma naught, gamma 1. Do we all understand the problem? Where is the confusion? I see some heads, one head shaking. What don't you understand about this problem? You don't know what
I don't know what I don't know.
you don't know what you don't know. Okay. Let's take it one step at a time. We have a parabolic trajectory, right? That's a given. And we want to know what should be the variations of the flight path angle, this gamma here. Right? Essentially gamma naught with time. For the passengers to feel weightlessness. Okay. The first thing you need to find here, or you need to understand here, is that what is the condition for weightlessness? Your acceleration should be equal to the gravitational acceleration, right? Or a component of your acceleration should be equal to gravitational acceleration. It depends on the direction, right? Or your acceleration should be equal to a component of gravitational acceleration. All of these different forms will work. It's just a mathematical game, right? So that's the first step. And we are moving on a path. If you recall, we had two different accelerations, right? We had a tangential acceleration and we had a normal acceleration, right? So play with those accelerations and see if they are in the same direction as the gravitational acceleration. If not, then find the components of gravitational acceleration, and you will essentially get to the solution. Did that help? Probably. So this is the first thing that you need to understand to solve this problem. But there is also a second thing you need to understand to solve the problem. And that comes from the the assumption we made. We are assuming that the Earth is flat essentially. There is no curvature to the Earth. I mean, there is a curvature, but we want to ignore it, right? What does this mean?
Zero normal gravitation. Curvature affected the normal acceleration.
Curvature, so curvature exists, right? So in your calculations, if you need curvature in a calculation, you should use the curvature, right? But what you should conclude from this, ignore the curvature, comes to the relationship between this d phi and d gamma. Since we are ignoring the curvature of the Earth, right? These two are equal. So changes in phi is going to be equal to changes in gamma, right? Which makes a lot of sense. Let's say you have this pen is the direction of your velocity. I'm moving my hand. This is d phi. And the changes of this angle, right? This angle of this vector has to be equal to changes of this angle here. Does it make sense? But if we were moving on a curvature, it would have been a little more complicated. So phi dot is equals to gamma dot. Okay, we are at the 10-minute mark. Do we have any winners here? I mean, there's no winners and losers, but do we have anyone who has solved this? No, that's all right. So, if you go back to the previous lecture, you will see that we defined something called the path, right? And it was just the arc length. That path is equals to what? How did we calculate this path compared to this angle phi? It's just the arc length.
Is it the velocity over rho?
That's s dot, right? That the path itself, if you recall, is just the arc length, right? So this is your path s from here. This is the center of your curvature. Rho phi is equals to your path, right? If you take the derivative with respect to time, this s dot is v dot. So v dot, or v, I'm sorry, is equals to rho phi dot, which is the same thing as, what was your name again?
Ross.
Ross, which is the same thing as what Ross said. So phi dot is actually equal to rho divided by v. And this is equals to the changes in the flight path angle based on the assumption we made here, right? Does this make sense? Okay. So we have one equation for the variations of gamma dot. Let's take a look at accelerations. So this is the parabolic path. We said we have a t and a n. How can we find the normal acceleration?
Is it v over rho? Is it rho over v?
I'm sorry, V over rho. Right, I'm sorry. That was my mistake. Right? Just error. Thank you. So, acceleration. Normal acceleration. How can we find the normal acceleration? No.
V squared over.
V squared over rho. Exactly. And we also have the relationship between V and gamma dot. Right? So keep that in mind. But how is this AN related to the gravity? They are not the same because they are not in the same direction. So it is the same as a component, essentially this component of gravitational force. Right? And how do we find this component of gravitational force? It's the cosine of gamma, flight path angle. So this AN has to be equal to G cosine of gamma. This is equal to V squared over rho. And we already know V is rho gamma dot. Right? So plug that in. Cosine of gamma is equals to rho squared gamma dot divided by rho, which means gamma dot is equals to, there's also a negative sign. Keep that in mind. AN is equals to negative of gravitational force. Or so gamma dot has to be equals to negative G cosine of gamma divided by rho. So the variations of flight path angle, or the changes in flight path angle with respect to time, is a function of your gravity, your original gamma flight path angle, as well as the curvature at that original. If you have that type of changes in flight path angle, you will experience weightlessness. Okay?
Gamma dot squared.
Gamma, yes. I'm sorry. If you look at your book, what they have done is that they have moved one of the gamma dot squares here to the denominator, and they have turned it to a velocity to make sure this is also a function of velocity, because we already know that rho gamma dot from here is velocity, right? Any questions? Yes.
So we're basically getting the trajectory from the curvature of the Earth because it's in line. Like we assume no curvature, but the road there is the curvature of the Earth, right?
Yes.
So we're basically just taking
Is it the curvature of the trajectory?
So is this equal? The curvature of the Earth is the trajectory of. Is that what we're assuming there basically, or how?
Is it? Think about it. Why not?
I'm just getting.
Because your trajectory does not
No.
strictly align with the Earth's surface, right? So it is not. It's not necessary.
That row is the curvature of the
Trajectory. Yeah.
Okay.
Earth is flat. Yeah. Aerospace engineers.
So for
Yes.
the normal acceleration, you have it equal to negative G cosine of the gamma. I just didn't know where you got the cosine of gamma from.
Pardon me?
I didn't know where you got the cosine of the gamma from.
So this is a component of gravitational force. Gravity is in this direction. We need to find this component of it.
It's going straight down, but you're at the angle.
Yeah.
Why'd you do the minus sign?
I got it from I just copied it from your book solution. So,
Because that's downward.
but essentially it should be a downward acceleration. Yeah. Yes.
I just got a kind of a general question. Is there an advantage to achieving weightlessness with inertial frame?
Advantage. It really. we have one comment here saying it feels great. So I've never experienced weightlessness, but I don't know if it feels great or not. But there is. I can't think of an advantage. Let me put it this way. I'm pretty sure there are situations in which. Let me put it this way. If you are a researcher, because we have this type of research, and if you can't go to the outer space to do your research, you can fly like this to experience the situation in the space, right? Weightless. There are actually videos on YouTube. If you remind me for next lecture, I will show you this experiment because it's already moved on. Okay, so let's move on. Let's talk about the Newton's second law of motion, or Newton's second law, right? What is the Newton's second law? Anyone? F equals ma. Exactly. Here, some of you actually already know this because you have had, or you should know this from your previous courses as well. But if you have had propulsion with me, you know how to calculate impulse. Or you know what impulse is. What is impulse? Force times time. But usually the definition is the integral of force from time 1 to time 2 with respect to time, right? Impulse is also equal to the changes in linear momentum. How do we calculate linear momentum?
Mass times velocity.
Mass times velocity. So impulse is equals to mv2 minus mv1, which is, I hope, I don't really assume this, because weird things happen. I hope you have seen this in your dynamics. We have all passed dynamics here, right? So I hope you have seen this in your dynamics, that impulse, or the integral of force with respect to time, is equals to changes in linear momentum. This is actually, you're going to see later, this and the next law that we are going to talk about are very important laws when it comes to orbital mechanics and orbit determinations. So make sure you remember this, right? We can have the same, or not the same, an analogous, how do you write this? Law for angular momentum. So we said linear momentum, changes in linear momentum is equal to impulse. For angular momentum, we first have to find the net moment. We define the net moment as r vector position, r multiplied by the net force, right? Which is also equal to r cross, that's the cross product, ma, or r m dv dt. This is the moment, right? Net moment on particle P, right? Any questions so far? Do we have any questions about the moments or the linear momentum or impulse. Just the definitions. Of course, there are some proofs for it, but we are not really concerned with the proof. Let's play with this part of it. Let's actually do this first. Let's say we are dealing with, we want to work on this. d dt of r mv. So just let's put this aside and let's work on this. Let's see how we can expand this. What is the expansion of this derivative? You have to speak up.
I'm sorry. It's dr over dt cross product of mdv over dt.
So this is, no. So it's essentially the same as d dt of a multiplied by b, right? It's dA dt plus dB dt, no, all of those. So we're going to get dr dt cross product mv plus r cross product m dV dt. And keep in mind that we are assuming m here is constant. If it wasn't, then it should be, we should take it into the derivative here. This part is v. Okay, dr dt. So we are going to end up with v cross mv plus r m dv dt. On one side we have, or one part of this right hand side, we have v cross v. What is the solution to this? 0. Because its v cross product of itself is going to be 0. So we'll end up with this d dt of r cross mv is equals to r cross m dv dt. If you look here, on the right hand side, we actually have this, right? I'm sorry, this. So on the right hand side here, we have the net moment, right? So d dt of r cross mv is equals to net moment. This is also a vector. Keep in mind that, don't forget the vector signs. Well, what is this inside the parentheses? mv part of it is linear momentum, right? What can we say about the whole thing when it is multiplied by vector r, the cross product of vector r and linear momentum? We can simply call it angular momentum, as we did with the moment. Moment is r cross the force, right? So r cross the linear momentum is called angular momentum. Have you seen this before? Angular momentum? Yes or no? Yes. Okay. So the changes of, and we are going to call angular momentum h, as I'm sure you have seen before. The changes of angular momentum with respect to time is going to be equal to the moments. Or we can actually take the integral of both sides, and the integral of moment from t1 to t2 dt is equals to changes in angular momentum. As you can see, this is analogous to the linear momentum, in which integral of f dt from t1 to t2 was equals to changes in linear momentum. Or there's no O here. Any questions? No? It's all clear? It's just a review, so I'm hoping you have seen before. If not, if it's not clear, come to my office. We'll talk about it. The next thing we want to talk about is the time derivative of moving vectors. So let's say we have this x, y, z. We have this coordinate system, and we have a rigid body that is rotating and moving. It's the same rigid body. Let's assume it's exactly the same. Doesn't look the same, but let's assume it is exactly the same, right? We have this vector A inside this body that is moving and rotating, or moving essentially. At time t, we have time t plus dt. Its magnitude doesn't change. Its direction is the only thing that is changing. And we want to find the derivative of A with respect to time. What do you think is this derivative, is the answer to this derivative? The magnitude of this vector is not changing. The only thing that is changing is the direction of the vector.
So that's 0.
So we have one person who is saying that this is 0. We have one person who says no. What about the others? What do you think? So magnitude is not changing, only the direction is. Yes.
Wouldn't it be omega times A, or cross product with A?
So we have one answer, omega cross A. What else?
I feel like it might be related to like the angle that it's rotating at, and so you times whatever the magnitude is by the cosine of the angle or something.
Okay, so related to the changes in direction, I guess, right? That angle and
Yeah.
direction. Anyone else? Okay. So it is not 0, of course, because if you recall, we said we have two important factors when it comes to vectors. We have their direction and their magnitude, and they are equally important. If it was just a scalar and its value didn't change, the derivative should have been 0, would have been 0, right? But since it is not a scalar, it is a vector, the changes in direction, it means that this vector is not the same vector anymore, because its direction is changing, right? There has been some change, right? The translational move doesn't really mean it. It doesn't change the vector, right? But if there is a rotation, there is a change in its direction, its angle. It is changing. How do we find this derivative? As your Gibson, right? What was your first name?
Horton.
Horton, I'm sorry. I forget your first name. Horton. As Horton said, we can actually find this derivative by the cross product of the angular velocity, which is related to the changes of its angle, right? changes of the angle and this angle is with respect to a reference frame. Can be any reference frame because we are interested in changes of that angle, right? So the angular velocity omega, cross product of the vector itself. So if we had a vector which value didn't change, but its orientation changed, its direction changed, then it is changing with respect to time, right? There is a time derivative. And that time derivative is equals to omega multiplied by a. And there is a bonus point here for you guys. And if you just go over the lecture notes posted, you actually can give me the answer to this bonus point. Prove this equation. Submit this bonus point by Tuesday next week, which is going to be 18th, right? Before the class. Okay? If you just go over the lecture notes, there's the proof there. You can just copy it. Make sure, I'm trying to understand it, and you'll get bonus. Okay. What if the value of vector was also changing? The magnitude of the vector. So time derivative of this vector A, it's a different vector A, let's call it vector B. Its direction and its magnitude is changing. Think of a car that is moving in a curvy road and someone is like putting more gas.
Would it maybe be like omega times like dx dt, dy dt? You are very warm. You are moving in the right direction. There is a dot. Where is this? Where is the dot product? So there should be a relationship. That the magnitude is changing with respect to time. The direction is also changing. If it was only the magnitude, then we would have said the changes of b over time, right? Whatever that is. If it was only the direction, it would be omega cross a, right? But both of them are present. So what we do is we just simply add them. That's it. How do we do that? And there is a very simple mathematical explanation for it. So we want to take the d dt of bxi plus byj plus bzk, right? What is the time derivative of this? The first component here. Just dB dt, dBx dt. Is that what you're saying? Yeah.
But the direction of I is changing, right? So di dt is not 0. Because I is changing. When the direction of a vector changes, it essentially means that its unit vector is changing, right?
Is it omega? Or omega x?
So this is bx multiplied by I, right? What is the answer to this? Let's say a and b are two numbers, two variables, two simple variables. dA dt b plus a dA dt. So based on this rule, which we just used earlier, what is dt d of this t over dt? dbx over dt I
plus bx
di over dt. Exactly. Thank you.
Is di dt the same as u?
The same as u?
Velocity component in the I direction.
No. So I here is a vector which value which magnitude does not change. Only the direction changes. So what is dIdt?
The unit, or the change in the unit direction.
This, right? Omega cross A. And here I'm going to use the big capital letter for omega because it is rotating with respect to a reference frame here, right? So we essentially have a reference frame X, Y, Z, a moving frame, right? This is called the inertial frame, a rigid frame that doesn't move. We have a moving frame, and we have the vector B from this moving frame. This moving frame essentially identifies the unit vectors for the vector B, I, J, and K, right? So the first component is going to be dBx dt I plus bx omega, and this is capital letter for omega, omega cross I. Okay? If you do this for all the other components, this dB dt is going to look like this. And I'm going to get all of the regular derivatives together. dBx dt I plus dBy dt j, dBz dt k, plus bx omega cross I, by, this is multiplied by omega cross j, and this is also a vector, by omega cross k. Since this is just a number, we can actually move it here, right? Bx, by, and bz are not vectors, are just components of a vector, just numbers, just a scalar. So we essentially can say, I can replace this, I'm gonna delete this, with omega cross bx I plus omega cross byj and omega cross bzk. Yes.
Is that last term supposed to be
BZ, yes, I'm sorry. BZ, exactly, thank you. So if you do this, if you move all of the B components just beside the unit vectors, this term will become just omega cross the vector B, which is something we expected, I guess we had from before. So, and the first part is called the derivative of B relative to this moving frame. Which is called this part of it, which is why this part of it is called dB dt relative, or rel. So, for a moving vector, which magnitude may also change, this will be the general form of the time derivative. Omega multiplied by b. Any questions?
Scroll up a little bit.
Sure. Is this enough?
A little bit more. Thanks.
Any questions? Yes.
So all those, like that box you circled, right, equals omega cross B, right?
Mm.
Okay.
Yeah. All of yes. Okay. Are we ready to move forward? Ready? Okay. And the second derivative with respect to time is also going to look weird. So be ready for it. This one is actually a little bit it's a little longer. The second derivative of vector b with respect to time is going to be the second derivative of a vector b relative to the moving frame, omega dot cross b plus omega cross omega cross b plus 2 omega cross db dt relative. The proof of this is in the book. This one is not in the lecture notes. So just do the proof. Just submit the proof next week, next Tuesday, and you'll get a bonus point. Keep in mind these bonuses are worth half a point. So by next Tuesday, you can have 1 point out of 100. I think they are worth too much. Your homeworks are worth 2 points. So, what is? We have already talked about this. Any questions? So, since we already know the time derivative of a moving vector, we already understand how to calculate this. We can actually talk about relative motion as well. Relative motion is exactly the same topic as before, talking about the time derivative of a moving vector. That moving vector is your position vector r. Okay? So we are essentially in the same inertial frame, x, y, z, and we have a moving frame, x, y, z. Think of this inertial frame as the center of the Earth. There's a frame on the center of the Earth, right? And the moving frame is a frame on the Earth's surface that is moving with your aircraft or a spacecraft or whatever that is. Okay? And there's also a particle, since we are only dealing with point masses, that is moving. And we have a vector r relative that connects the origin of this moving frame to your particle. And we have an RO that can, or R naught, that connects your inertial frame to the moving frame. And your vector R itself connects the center of inertial frame to the particle. So based on this figure, I assume you can deduce that R is equals to vector R is equals to vector R naught plus vector R relative. The velocity vector is going to equal to V naught plus dr relative with respect to time. And this dr relative is that B vector we were talking about, right? Which direction and position, which direction and magnitude can change. V naught is the velocity of your inertial frame, if it's moving at all or not. So, this velocity vector is going to be equal to omega multiplied by r relative. That's omega cross your relative vector plus v relative, which is dr dt relative. Let's pause here for a little bit and take a deep breath. I feel like you are getting a little bit confused because of all of these derivations that are there. Is this true? Okay, it is true then. So let's pause here. We are gonna start from the relative motion again next week, and we are gonna finish the first chapter on Tuesday. But for the rest of the class, we can't solve an example. We can start this solution at least. Right, this is going to take a long time. This is going to take time. I can give you this as just a quiz. Let's solve it together. Let's start the solution. Let's just start thinking about it. So next Tuesday, we're going to come back to this example. We're going to finish the example, and then we'll move on to the relative motion and the numerical methods. Are we familiar with this numerical method? Its German pronunciation is Runge Kutta. I've actually searched this. But most people here call it Rang Kutta or Ranch Kutta. Are we familiar with this method? No. Have you even heard the name of this method? No. What did you have? What did you learn in the numerical methods course then? Nothing.
I remember it. I don't remember what it is, but I've heard it.
You have heard the name.
Yeah, I just don't remember how to do it.
No, that's all right. I just want to make sure that you have heard the name. Well, so next Tuesday we are going to 11:14. Let's not start the example. Let's just talk about next Tuesday. And we are going to do the relative motion. We are gonna essentially talk about the acceleration or velocity of an object that is moving close to the surface of the Earth, like an aircraft or a spacecraft that is orbiting the Earth, right? We will just find the formulas, like the acceleration and velocity, and then we will talk about the numerical methods. We will go over the Runge Kutta or Runge Kutta, whatever, however you want to pronounce it, doesn't matter. Methods. I will give you a example in MATLAB on how to use the Runge Kutta method if we have enough time. I'm not sure because I don't know if we can finish all of this in 1 hour and 15 minutes. But if not, then we'll continue on Thursday.
We should have our laptops ready then.
Yeah, if you wanna, yes, that's probably a good idea. If you have, do you have MATLAB on your laptops? Yes,
Yeah.
because I think university gives it out for free, right? So
Sometimes you have to have a little fun time with IT to get it, but you can get it.
that's a very good thing to consider. That sometimes if you don't have the MATLAB installed on your laptop already, you may need to go to IT as soon as possible to have it ready by Tuesday because it may take time, right? Okay. Do we all have MATLAB on our laptops? Do we all have laptops? Let's first ask this. Yes. Yes. Okay, good. So bring your laptops with MATLAB next Tuesday, and we are going to work a little bit numerical methods, and that will be it for chapter 1 of this class, I guess. Enjoy your weekend and stay safe.